So thank you, Professor Pattanaik. Welcome back, all the participants. So this is a course on microfabrication, and I am going to talk to you about a wide range of microfabrication techniques, which are particularly for polymeric or soft surfaces. But now, with the advent of different type of new materials, they are also becoming very, very important. Uh, and so, what I understand from the international speaker, you must have heard by now about fabrication, one of the key techniques of microfabrication, that is photolithography, in different contexts. But I will try to highlight to you some, first, what I will do, some very generic applications of patterning, which is beyond device fabrication, but there are many, many other domains where patterning, micro patterning, or nano patterning is important. And I will then show that there can be some very frugal, deep in science techniques which can be used, combining the essential concepts of fluid dynamics, some instabilities, interaction between surfaces. We can create meso and nanoscale structures. So patterns are basically regular arrangement of objects. A whole lot of patterns can be seen in nature, many optical patterns, many structural patterns. Some of these you can see. I can actually talk for an hour on different types of patterns that are available in nature, but that's not the focus of today's talk. So we are going to focus more on micro and nanoscale structures on different surfaces, and which leads to several interesting functionalities. For example, many properties of material can be tailored by the presence of patterns on surfaces. One of them is, I will talk in little bit detail, is hydrophobicity of the surface or superhydrophobic surfaces, structural color, and then other optical applications and so on. Uh, Moving on, so let me just give you a very simple example which is known to all of you. Is if you look into these buildings now in most cities in India and abroad also, you find tall buildings with glass facade, and these glass facades are always shining. But as students, you all know that if you leave your bicycle outside for 5 days, it gathers a thick layer of dust. So what is the secret? Because you do not really see people always cleaning them dangling from the top. It turns out that they have some self-cleaning coating. So the whole idea is that you create some structures and along with some low surface energy coatings, which basically enhances the contact angle, the equilibrium contact angle of a drop of water. So this, if you put a drop of any liquid on a surface, it takes a hemispherical shape, and the shape is defined by sort of the balance of the surface and interfacial energy of the surface and the liquid. So one of the thing is that if you try to put a high surface energy liquid on a low surface energy surface, of course you see very high contact angle. An example is if you have ever accidentally broken a thermometer at home or somewhere, you see that the mercury, which is a liquid that comes out and rolls on any surface like a metallic ball. But what you can also do, but if you put water, let's say on a table or on a bench or whatever, you see that it's spreading quite nicely. But what you can do is, by the presence of the structures on surface, you can enhance the contact angle of liquids like water. One very classic example, and I am standing and talking from NIT Silchar, which has a lot of water bodies filled with lotus leaves. And you can see, even I just stopped by one of them, you see a lot of tiny droplets of water resting on the lotus leaves. So what happens is, lotus leaves grow on the surface of the pot. So let's say if there is a heavy rain and water accumulates on them, they will simply drown. And that will hinder their photosynthesis and other their metabolism. So nature has provided them with some structures which make them sort of hydrophobic. So water sort of splits up into droplets and it simply rolls off. This is what is known as superhydrophobic phenomena. Or there are the concept of structured hydrophobicity. So basically there are different wetting states like Cassie and Wenzel state. You can look into it in details. Even a very classical mechanical or chemical engineering concept can be the condensation, phenomena of condensation. Many of you probably know that when condensation starts, it starts off with dropwise condensation, and then eventually it transforms to film type condensation, which leads to or enhances the resistance to heat transfer, and the condensation efficiency sort of drops. So, but why does this happen? Because nucleated drop starts to populate at large areas, and the drops sort of join up, leading to a film. But think of a situation if you can have these drops which are forming, they immediately roll off. The surface remains sort of empty, it does not get covered with a film. So your heat transfer or condensation efficiency you can increase. Not to forget that corrosion is a major problem in metallic material, particularly iron. And one of the necessary conditions is crevices and cracks. Water gets entrapped, and because of oxidation, corrosion happens. So if you can cover these surfaces with some sort of coating or structures which prevent the accumulation of water, then corrosion, which is actually causes colossal damage to GDP, many buildings and structures in coastal areas get damaged. So that can all be hindered. This is another very nice and important example. So we see, at least in our country and many parts of the world, a lot of PV panels or solar panels are being installed across everywhere. And all solar panels, so most of you probably know that these solar panels are made of silicon, but generally they are covered with a glass. So they have a solar panel cover. And in a country like ours, what happens is there is a lot of accumulation of dust on these layers. So what happens is now, because of this presence of the dust layer, it sort of prevents the light from reaching the active layer, leading to a significant drop in efficiency of the panels. And often you see that these solar panels have to be cleaned. Now, solar panels normally you would install in large areas which is uninhabited, nobody goes there, in deserts, end of runways, top of buildings. But if people have to go there and clean them manually, that sort of partially defeats the purpose. So again, there is a lot of work that is going on to come up with some coating on these surfaces which makes them hydrophobic, so that the water, you can sprinkle some water from the top and then automatically it rolls off and it gets cleaned. Another example is if you have seen these compact discs, the data storage discs. If you have ever seen, now it has become obsolete, but in our generation, all of us have seen. So if you look into the backside of a data storage disk, you see some rainbow colors coming in, right? Now this rainbow colors is not, and if you change the angle of tilt, the location of the color also changes. So the normal perception of color that we have is primarily based on absorption and reflection. So if something is looking blue, you know that it basically reflects light corresponding to the blue wavelength, and every other wavelength it absorbs. But here you see the colors because of diffraction, the phenomena of diffraction. Why it happens? Because you have some features on the surface over here which have sizes which are comparable to the wavelength of visible light, and therefore when light falls it sort of gets splits up, because as science graduates, engineering students are all science students, you all know whenever you see rainbow color, basically white light is getting split up into its original components. That happens in a prism based on the difference in their Ri, but here there is no prism. So what happens is, because of diffraction, they get split up, and this happens particularly because of the presence of some structures. Another very nice example of structural color is some beautiful coloration in beetles. In fact, it turns out there are some pioneering work by a group from Cambridge University which have shown that we all know from our basic biology lessons that insects have compound eyes, but it turns out that insect vision is not only compound eyes, they basically recognize a colored surface based on the structure that is present on them. There are many other applications, beautiful examples where, for example, this water spider can delve deep into water, right, to catch fish, a fishing spider, because of the fact they have some hairy legs and oxygen gets entrapped over there for a long time, giving them the ability to breathe from that stored oxygen. Water striders, a small tiny insect, can walk over water, which I and you, being the supreme animal in the world, we cannot do it. House lizards can climb along the walls, you have seen it, but If you use a sellotape or an adhesive tape, you can use it maximum twice. After that, it becomes bad. So they are all happening because of presence of patterns on surfaces. This is also another beautiful example, the chameleon, where there is this color changing lizard. So it had always intrigued many of us whether they actually change color or not. The ground reality is yes, they do change color. The Indian version, you see, they mostly change color between brown and green. This is an exotic version from somewhere in Masai Mara. You can see it is actually, this person is a great photographer. So he actually captured when the lizard was changing color. And how do they change color? Because we cannot change our skin color. They basically change color by sort of modulating the surface structure of theirs. So it's partially structural color. There's a lot of deep science. I will not go into that. There are many optical applications. For example, most of the spectacles that comes these days, they come with some smart coatings. They might come with anti-reflection coating if you are driving in the highway at night. If you continuously come out in and out of air-conditioned office, you would like to have an anti-smear coating. If a child or kids have to wear spectacles, maybe the parents will go for an anti-scratch coating. And many of these functionalities, optical properties, are attributed to coatings, thin layers, and many of them have structures over them. Having said that, we already talked about some of the superhydrophobic surfaces. So they are also very important in aircraft. They are flying. Particularly aircrafts fly at very high altitude where the temperatures are very less. So if, for example, freezing happens at those temperatures, that can lead to disaster, complete disaster. You are mechanical engineering students, so airspeed is monitored by pitot tubes, right? And if there is freezing at the tip of the pitot tube, that might lead to significant damage or stalling of the aircraft. So the aerodynamics and many other things also depend on whether the surface is hydrophobic or not. Another very simple example of this liquid repellent surface is the non-stick cookware that we often use at home, where you see that even oil does not spread, and therefore any food item that you are cooking very nicely comes out. But what is the biggest application area of patterning? And I'm sure the Professor Faizul Muhammad Sabri has already talked about it. It's in the device fabrication. So if you ever wondered that how these computers becoming sleeker and sleeker and they become faster and faster with higher storage space, it's not because of some great development in computer science, but it is due to some great development in material science, right? So basically, to cut a long story short, computer chips are becoming faster, and that is computer chip at the heart of it is basically array of PN junctions. So if you can make the domains narrower and narrower in the same area, you can pack more number of junctions and making faster processors. So these are some interesting numbers. Probably most of you were not born, but we have seen this evolution. Like having a PC, a Pentium PC was a great thing at one point of time. Now I think it's i7 core. We have almost all the functionalities of a computer available in your cell phone now. Earlier, 20 or 30 years back, we just had a phone that could barely send some SMS and make a phone call. So most of them are all these. Every smartphone has a display, smart display, right? Touchscreen display, and all these developments. They are all attributed to development of one major technique. I'm sure it has already been discussed. It's photolithography. So basically, what it does, photolithography at the heart of it is a light-based. Light is UV light generally, and there can be other types of light. And again, you use a very special type of material, which is actually a polymer, a photosensitive polymer called photoresist. So the whole idea is that this photoresist, upon exposure to light, changes its properties. Now, depending on the tone of the photoresist, whether you have a positive photoresist or a negative photoresist, it might actually enhance its properties, or its property might degrade. And basically, so what you do is you have some hardware element called a mask, which selectively allows the light to pass at certain locations, and at certain locations it does not allow the light to pass. You basically take a photoresist layer. Generally, if you are fabricating device, it's on silicon or oxide coated silicon. Place the mask and then expose it to light. and then you sort of remove the weakened part of the photoresist. So you get the structure that is drawn on the mask, now physically transferred into the photoresist layer, and then subsequently you do the post-processing in terms of etching, etc., followed by eventually doping, leading to these PN junctions and whatever. Now, I am sure what has already been discussed in this course, that for device fabrication, solid state device fabrication, this is basically essential, or for chip making, this is essential. And it is a very well established technique, and I am not going into the details of the technique. But if you look into this particular slide, here are the key elements of the process. If you sort of look into these things carefully, you will get a lot of idea about the process and in a very simplistic manner. I mean, this is a billion-dollar industry, so there are a lot of work that is happening in these areas, and top companies like Intel and companies in Taiwan are based in it. For example, spin coating itself is a topic in which I can talk for 2 hours, which is basically used for coating the photoresist layer over your silicon wafer, and so on and so forth. Now, so here basically what I told, that you have a mask and through which you pass the UV light, and depending on the type of the photoresist you are using, you might get a positive replica or a negative replica, and subsequently you do the post-processing. This is very, very standard, but nonetheless, there are certain limitations I'd like to highlight. One of them is photolithography, right from as the name suggests, can pattern only a photoresist layer. So it's very material specific. There are different types of photoresist, but at heart, photolithography can pattern only photoresists. It requires very high-end infrastructure like yellow room and mask aligner and stuff like that, which are okay for device applications, because you are going to make a computer chip, for example, and which you are going to use in your phone or computer, which you are going to sell at a premium and going to use for 5 years or 10 years maybe. But there can be many, some of the examples I gave, there can be many bulk nano applications of these pattern surfaces, where if you try to do photolithography, it really becomes exorbitantly expensive. And as I also told, that it is only capable of patterning a photoresist layer. But there can be so many other type of polymeric material, including polymeric material, which you may want to pattern for doing some nice experiment or work or low-cost diagnostic devices, where photolithography may not be the best suited techniques. So with this, so for example, some examples I will give. So we talked about dispensing a drop on a solid surface and it takes a hemispherical shape. But instead of that, if you put a liquid drop on a grating pattern substrate, its shape changes from a hemisphere to an ellipsoid, right? This is what is called, this is a very simple example which all of you are understanding, you are seeing also. But this is what is called a directional wetting or anisotropic wetting. So here what it means, because of the presence of the surface structures, the liquid is spreading favorably in one direction and not spreading favorably in the other direction, in the transverse direction. So very simple thing, if you, let's say, have a drop like this, you tilt it in this direction, the liquid drop will roll off very easily. But if you tilt it in this direction, the drop will not roll off, right? So there are a lot of people who are interested in dynamics of these type of systems. So these are where the basic objective is to study let's say, evaporation or dynamics or rolling of the liquid drop. And if you want to have a photolithography facility as a backup for doing such simple experiment, it becomes very difficult. Similarly, there are a lot of works that happen that are where people are using these structured or patterned surfaces for modulating cell behavior, wound healing, and stuff like that. And there, for these living cells, in the previous session when I was talking about atomic force microscope, there were discussion on bacteria and cells. Again, you might require special type of biocompatible polymers or material over which the cell may grow preferentially. So having again a photoresist layer may not be the best idea. So with all these concepts, it's around mid-90s, there are two pioneers, I would say, roughly at the same time, George Whitesides from Harvard and Stephen Chow. Earlier he was in Minnesota and subsequently he is now in Princeton, who came up with a series of techniques which are capable of creating meso, nano, and micro patterns on different type of polymeric surfaces. And unlike photolithography, which specifically talks about a very well-defined technique, the word soft lithography, there is actually no technique called soft lithography. Soft lithography is a suite or ensemble or collection of various different techniques which can be used for patterning different type of polymeric material or soft material in a nutshell. So this whole area started in mid-90s and it is still evolving. There are a lot of people who work on this. But the golden era of soft lithography was mid-90s to mid-2000, where there are multiple publications in Nature and Science. So they are basically techniques rather specific towards soft surfaces like polymers and gels, as well as for application which do not require extremely stringent quality control or defect-free patterns like in microelectronics. There are several application areas where large area, meso and nanoscale structures are necessary. But even if there are some defects here and there, it's actually fine. Sensors, biological applications, structural color, textured hydrophobicity, progress in all these areas depend on availability of robust, simple, easy to execute, and most importantly, cheap patterning techniques that can create large area structures over large areas, centimeter square areas, right? And ability to create should be reasonable. And most cases, the concept works. So basically, I'll come to this. So as I told that there is no specific technique called soft lithography. There are different type of techniques, must be some 1,000 names you will find which are all patented and published and well known, but I will give you glimpse of some of the major techniques, maybe 4 or 5 techniques. And then towards the end, I will tell you about how we are also looking into some of the soft lithography techniques and creating some structures which are beyond the obvious, which are not exactly, which is very common. You can, in principle, have 2 types of patterns when we talk about patterns. They can be either topographic patterns, let's say line grating, hills, pillars, columns, whatever, or you can also have chemical patterns. Do you know some examples of chemical patterns? In fact, the easiest example of a chemical pattern is a printed sheet or any writing, because basically there is no topography, but you dispense ink in such a manner. So professor was talking about inkjet printing. He was emphasizing on the nozzle part of it. But ultimately, what does it create? It does not create a topography, but it basically covers some area of your sheet with some material which has, or this ink in this particular case, which have differential optical properties. So some places you see some structures. So all alphabets actually are some patterns which you are taught to replicate the pattern in a particular manner, and that we have the ability to read. So basically, we can have 2 types of patterns, chemical patterns. So other than printing, the other very interesting example of a chemical pattern can be alternative domains of hydrophobic and hydrophilic domains. So you can have a hydrophilic surface which likes water. You can have a hydrophobic surface which does not like water. But artificially, based on some of the soft lithography techniques, it might be possible for you to create structures where you have alternating domains of hydrophilic and hydrophilic patches. So basically, when we talk about these patterns on soft surfaces, one way of distinguishing or discriminating them is by the nature of the patterns. So you can either have topographic patterns or chemical patterns. So here are some examples, and morning, those of you who were there, you can see this is actually an atomic force microscope image with a mistake because the vertical scale bar is not there. You should remember that. Now, how to get them? So in most cases, what was written in the previous slide, in most cases what we have is we have a stamp, right? And you actually create a replica of the stamp on the soft surface. Now many of you have seen Indian sweets, right? And many of them come with some design. So what exactly is done? You take the casein or the chena, and then you have a mold. And many of you have done some of these in your childhood also. You have a mold. You press a soft material against it, and you get a negative replica of whatever mold you have. This is in principle how this replication works. So what is the necessary condition for the replication? The material that you are trying to pattern is soft, and that is meeting our requirement over here, right? So again, so basically, so I'll come to it and explain it. What it means is that you might have a stamp like this. You take it and press it against a soft layer, and you get a negative replica of the stamp. One more example that one can talk about is, for example, the rubber stamp, where you have a negative replica of the alphabets that are there. You ink it and just press it on a sheet of paper, you get that print, right? Little bit of some formal discrimination I would like to tell, but this probably will not make sense to you right now, but we will understand it in few minutes time. So one can also discriminate the techniques based on the nature of the stamp, which can be a rigid stamp or a soft stamp, flexible stamp. I will come to it. And then this part of the discrimination you already understand. You can either create topographic patterns or you can create chemical pattern, right? Now what follows is I will talk about certain specific soft lithography techniques, which are the very popular ones, right? And give you an idea so that you understand how exactly this pattern replication happens. So some of them that we are going to take up are nano imprint lithography and few of those. And I can assure you that towards maybe after half an hour or so, most of these techniques will make sense to you. Okay, so before I move on, let me introduce you about a very special type of material. It has a commercial name, Silgard 184. It's a cross-linked polydimethyl siloxane. It's a very special type of a polymer. It's also an example of an inorganic polymer, because whenever we are talking about polymer, basically what we know that we have a carbon-carbon backbone, and carbon can participate in polymerization because carbon hybridizes. But alongside carbon, silicon also hybridizes, and therefore it is possible to have silicon-based polymers. Of course, the backbone is not carbon-carbon like silicon-silicon. You have an SiO-SiO-Si backbone. And so basically the silicons participate in polymerization, chain formation, the oxygens do not participate. So there is a gap because of the presence of the oxygen atom between adjacent silicons, and that sort of makes the material very flexible. So what is this material? This material, sorry, one slide is missing, comes in two parts. So the first part is part A, they call it, it's oligomer. What is oligomer? It's few chains. It's not a long chain polymer, but it's a few chains of the monomer, right? And part B is the cross-linker. So a cross-linker, from the name itself, it's clear that if you add this and do something, what is that something I will tell you, you basically create a cross-link matrix. So the other thing I'd like to quickly tell outside what is there in the slide or the PPT is that there are examples of plastic and polymer everywhere, right? So most of you, the pen that you are using is a plastic, right? But if you look at them carefully, they are not deformable, right? But there are some polymeric material, for example, like a rubber band, which is stretchable, which is elastic, right? So there is a very fine distinction between the two types of polymer. So these type of polymer, which are solid like at room temperature, they are called the glassy polymers. Now, why they are called the glassy polymers? Because as you know, Most solid materials are crystalline, right? Most metallic materials are crystalline. But glass is, I guess you know, it's not a crystalline material. It's an amorphous material, right? But then how is it sort of solid at room temperature? It is, glass is often called as a supercooled liquid. So because of the fact the molecules, so amorphous means the molecules are random, but at room temperature their viscosity is so high that the molecules cannot sort of change their relative position. Therefore it behaves like a solid. And you must have, so what is the distinction between a solid and a liquid? If you, we all know that solid has definite shape and liquid takes the shape of the vessel that you pour it in, etc., etc. But if you look from a slightly different perspective, I can also say the difference between a solid and liquid is, in solid the adjacent molecules do not change their relative position or cannot change their relative position, whereas in a liquid the adjacent molecules do change or can change their relative positions. And this basically translates to two things. That means solids are non-deformable, liquids are deformable. And those of you who were present in the morning, we talked about the interaction forces. It also makes it clear that the intermolecular interaction forces in solid is the strongest as compared to the liquid. What is a gas? For a gas, the mean free path is infinity, so there are no neighboring molecules, right? There is no interaction. Now, when giving the example of the rubber band, you all know it's elastic. So it is made up of a very special type of a polymeric material which are elastic in nature or called elastomers. So what are those? So if you stretch a rubber band, how or why is it getting stretched? Because you are supplying energy from outside. From where are you supplying this energy? You are supplying your own metabolic energy. So you have all seen that you take a rubber band, it stretches, right? Now you withdraw the force and it relaxes back to its original configuration, right? This all of you have seen. So what is basically happening? The energy that with which you are deforming this material is not getting dissipated. It gets stored within the matrix itself, and when the outside or external source for this deformation is withdrawn, this energy is released back, and therefore the material goes back to its original configuration. This all of you must have seen. Now, how this is possible? Why it does not? But however, if you pour liquid, it simply flows away, right? So what is the difference? Difference is, in a liquid, there is no bond formation between the molecules, and therefore it can flow away, it can dissipate. But in an elastic material, basically the molecules are stitched or stapled with each other in the form of crosslinks, right? So that is what makes it elastic. Now, coming back to this particular material, what we have here is a oligomer, which is a liquid, high viscosity liquid, and the crosslinker. And what you do, you mix them and you put it for thermal annealing. So you just cure them for 120 degrees centigrade, 4 hours or 6 hours. And what happens? So during this thermal annealing, the crosslinks grow between the adjacent chains, resulting in a crosslink network, right? So basically, it's something like this. You start off with this individual chains, and when you thermally anneal, it forms these crosslinks, physical crosslinks, which gives them the elastic nature, right? And how does it happen? It happens when you thermally anneal this thing. This is important for the subsequent discussion that is coming up. That's why I spent so much time and emphasized on this. So the first technique we are going to talk about is replica molding. Once you hear about it, you will feel it's child's play. But this original work was published in the journal Science. So what you take is, you take a pattern, block like this, lithographically fabricated. It can be created by photolithography or somewhere else. And then basically you take this liquid. What is this liquid? This liquid is a mixture of these two, right? Now, initially, when you mix and you do not heat it up, it behaves like a perfect liquid, high viscosity liquid. So you take the liquid and simply pour it over this mold, right? And you make some arrangement so that the liquid does not flow away, drain away, etc., etc. And then you put the whole thing for thermal annealing, right? So I hope you are clear by now. As you do thermal annealing, what is happening? There is cross-linking or solidification of the polymer that is happening. Now, as it solidifies, it is solidifying in presence of a structured surface. So whatever structure was there gets replicated on one of the faces of this block. And it's a flexible solid. So after your annealing is done, you can simply peel it off manually. And in the process, what you have created is a negative replica of the original pattern. But remember one thing, you have created a perfect negative replica, right? So this sounds like a very, very simple technique, very obvious technique, but ground reality is when it was sort of published or people did not know. So in 1995, around 1995, a pretty recent work to be very honest. And so this is one of the most widely used soft lithography techniques, I would say, which is known as replica molding. Now, I was talking about the other type of polymer, like these polymers that are solid-like at room temperature. So they are more like amorphous material or glassy material. So what does it mean? They have long chains which are sort of entangled with each other. Basically, what is entangled? So if you have taken noodles, for example, you must have seen that the threads of noodles, they are sort of intermixed or entangled like that. And that sort of makes the flow of individual or movement of individual thread very difficult. Same here. So because of this large number of molecules which are entangled with each other, it is not amorphous, but it sort of behaves like a solid at room temperature. Now, what you can do, or you can all understand, if you take some of these plastics and simply heat it up, what will happen? It will soften after some temperature. What is this temperature after which it softens? It's called the glass transition temperature. Basically, because of its analogy with the way the glass behaves. It's also an amorphous solid. This also is an amorphous solid. So here, what we do, we again take a stamp, but this stamp is on a rigid material because there is a reason for that. And what we take is we take a polymeric layer over here, which we heat it up so it becomes soft, press the stamp hard with a lot of external pressure, cool it down, so again it becomes rigid, right? And now withdraw the stamp, right? So in the process, again, you have been able to successfully create a negative replica of the original stamp pattern that was available with you. This technique, again, a very simple technique, but this technique is called nanoimprint lithography. This technique was invented in around 1996 by Stephen Chow, not from Whiteside's group. Two things here. Unlike replica molding, the previous technique that we talked, which again was very material dependent. Material dependent in the sense that it only works for a thermocurable elastomer, because you needed a material which, number one, is liquid at room temperature so that you can pour it. Then when you do a thermal annealing, it must cross-link and then only the patterns form. But unlike replica molding, this works for a lot of material, lot of glassy polymer which are very generic in nature. Generic in the sense there are many glassy polymers which are solid-like at room temperature, and generically once they are heated above their glass transition temperature, they soften down. And this technique can work for all those type of polymers, not limited to any particular material. Only thing that might differ from material to material is the exact value of the glass transition temperature. Even for the same polymer, depending on the molecular weight or the chain length of the polymer, the glass transition temperature may vary. Because if you have a longer chain polymer, you probably will understand the effect of entanglement will be higher, and therefore you will actually need to supply more energy to make it soft. So why does this softness happens, or what exactly is meant by the softness? Softness means, again, the molecules, so the material can deform. Deformation, now, if you are listening to me, it means that the molecules can move from one place to the other, so they can change their relative position with respect to each other, right? So this, how is it possible? This is possible only when the translational kinetic energy of the molecules is higher than the interaction energy. The van der Waals force we were talking in the morning is higher than that. So anyway, I will not go into the details and make the things difficult for you. But here is another technique by which you can create a negative replica. Again, that is a very important thing. A negative replica of the original pattern on a glassy polymeric material. So there are certain advantages, as we have already seen. This works for a large number of materials, not limited to either photoresist or Silgard or whatever. But there are some limitations and critical issues. So we have to use high temperature, and more importantly, we have to use high pressure, because when you saw the video running, you must have noticed, maybe let me run it once. Your understanding. So you bring in the stamp from outside and then apply pressure from outside, right? So that pressure is required, and therefore that is the reason why you require a rigid stamp, so that it can withstand the pressure. More importantly, I know I am talking to large number of mechanical engineering students, so there is also very interesting hydrodynamics that is associated with this pattern replication. So what you are doing is you are bringing in the stamp, right? And you are pressing it against a semi-solid layer. So this deformation is happening, means it's showing a plastic behavior or liquid-like behavior. Now, where exactly the deformation is happening? So when you apply the pressure, basically the polymer over these areas are sort of getting squeezed out, and it is sort of rising through the cavity part or the recessed part of the stamp. Now, please understand that the stamp is coming down, whereas the polymer is basically going up. And probably you have all heard in your fluid dynamics lessons about the no-slip boundary condition. So you see here, as the stamp is coming down, the liquid adjacent to that has a velocity towards the below, whereas at the central part, the liquid is rising. So the velocity gradient is actually very, very high. And what does velocity gradient lead to? Velocity gradient leads to enhanced shear stress. So basically, these patterns that are created by nano imprint lithography have a tendency to contain a lot of residual stress, which is not very good, because subsequently this stress, the material tends to or tries to release this stress, and which can lead to pattern damage and associated problems. There is another way of achieving the same effect, and that is by solvent vapor exposure. Now, I will spend a minute on a very interesting, very fundamental problem. Now, if I ask you a question that, let's say, sugar dissolves in water or salt dissolves in water, but sand does not dissolve. So what is the reason for that? The reason for that is, if anything dissolves in something, so basically from a molecular standpoint, it is thermodynamically favored for the solute molecules to be surrounded by the solvent molecules. This is the necessary condition for solubility. If somebody somewhere has come across that intermolecular space is large, small, that is all useless concepts. So if something is to dissolve in a liquid, that molecules of the solute must be willing to be surrounded by molecules of the solvent. This is the whole idea. So now you know in a minute's lesson that sand molecules do not want to be surrounded by water molecules, and there can be many ways you can explain it, thermodynamically, spreading coefficient, etc., etc. I'm not going into the details. If you want to delve deeper, you can look into the net. So what can be done is these polymeric film that you create for nano imprint lithography. What has been done here it has been heated above the glass transition temperature so that it sort of transforms into a liquid state. But instead of that, another approach, a more benign approach, benign in the sense that you really do not need high temperature, is to simply keep it in a chamber which is saturated with, it's a very, I mean, apparently it will appear to be a little complicated, but it is not complicated. You just put it in a chamber which is saturated with solvent vapor. So let's say your polymer A dissolves in solvent B. You know about solvent from your chemistry. So you put it in a chamber which is saturated with solvent vapor. Now you know that polymer A wants to be surrounded with the solvent molecules. So what will these solvent molecules do? They will simply penetrate into the matrix by the process of diffusion. And as they penetrate between the molecules of the solute or the polymer, opening up space or creating more space. And as the gap between the polymer molecules increase, so that leads to some sort of swelling of the film and basically softening of the film. So just by, and there are formula by which you can sort of calculate the extent of swelling and other things. Again, it is all here. You can, if you find it interesting, you can check it. So what do we basically do? We basically first put it in a solvent chamber, swell it with the solvent molecules. You don't have to do anything. It's by the process of diffusion the molecules get in and get swollen. And then you bring in the mold or the mask and press it with the pressure that we talked about, and you get a negative replica. And what needs to be done here? What needs to be done here is that while the mask or the stamp is in contact, it has to be removed away from the solvent chamber so that the solvent diffuses out, and basically you get a negative replica. So basically this is nanoimprint lithography, but it is solvent vapor assisted nanoimprint lithography. I know that this might appear to be something which is slightly new and heavy, but if you follow carefully, this is nothing is difficult. I teach it regularly at IIT Kharagpur to my undergraduate students. There is another technique that has become very popular over the years, which is known as capillary force lithography. Concept is very similar to nanoimprint lithography, but instead of a rigid stamp, you actually use a flexible stamp, a PDMS stamp, the stamp that is itself created by replica molding, right? So what is the concept here? The concept here is if you bring the stamp in contact with the film, right? You do not heat up a priori or apply pressure or anything like that. You bring the stamp in contact with the film, and then if you liquefy the film, right? How do you liquefy? You now already know two techniques to liquefy the film. Number one is you can heat it up and liquefy. Number two is you can expose it to solvent vapor and liquefy. If we liquefy the film, then since the stamp is sitting on the film, the walls or over the walls of the stamp, you can observe a rise of the liquid meniscus due to capillary action, right? So again, so basically if you give adequate time, there is complete mold filling by capillarity. Now what is the advantage? The advantage is twofold. Since you are now achieving the pattern replication by capillary action and not by viscoplastic deformation of the polymeric layer, you do not have to apply force from outside. This is the advantage number one. And secondly, since you are not applying force from outside, you do not need a rigid stamp, right? Because you needed a rigid stamp in nanoimprint lithography so that it could withstand the force or the pressure that you are applying from outside. So here what you can do is, it's now a sort of a circular thing. The stamp that you might have created by replica molding here can itself be used for subsequent patterning of other type of glassy polymer films. And all you have to do, you bring in the stamp in contact with the film, and then you either take the film to a liquid state, either by thermal annealing or by solvent vapor exposure, and then pattern replication takes place. There is another big advantage which I did not highlight previously. Since you are using a flexible stamp, so after pattern replication is over, you can simply peel off the stamp and throw it away. Whereas here, the way I presented, it appeared to be very simple, but in reality it is not, because you after all bring in a rigid stamp, press it against a polymeric layer to achieve the pattern replication. Now the question to ask is, how do you remove the stamp? Because you are also telling that you have to cool it down. And mold breakage in nano imprint lithography is a major problem. So though not up to the level of photolithography, but nano imprint lithography also requires pretty robust and significant hardware. Whereas in capillary force lithography, it is a really frugal technique, because if you have a flexible stamp, you can simply use the stamp for pattern replication. Just the temperature or solvent vapor exposure is required to take the polymer, the glassy polymer that is here, the polymer film that is here, to the liquid state. And then pattern replication happens due to capillary driven flow and not by viscoplastic deformation. So now we are at the halfway of our lecture, and I will take you back to this slide again. And now you see that this slide now makes much more sense to you than 20 minutes before. So now you see we talked about having two types of patterns, chemical patterns and topographic patterns. So far, I have limited my discussion to topographic patterns. Chemical patterns is coming up. But more importantly, there are some terms over here which now make sense to you. For example, nano imprint lithography now makes sense to you. And when I write it's due to viscoplastic deformation of a polymer, that also you understand. You find replica molding over here, which makes sense to you, right? You also find capillary force lithography, which makes sense to you, right? So you see already some of the key soft lithography techniques. Probably the word soft lithography you heard for the first time at 3 p.m. today, you are already making, understanding some of them. And these are really advanced areas of research where a lot of active research is happening even now. Moving on, as engineers, you probably know that processes can be defined in several ways, and one of the ways is it's a batch process or a continuous process. And industrially, we always would like to have continuous process. But all this lithography and fabrication, whatever we have been talking, are essentially batch process. So you take one surface, coat it and do something and then take it out. So people started to think, can these pattern replication or soft lithography can be made continuous? And that led to the development of what is known as roller nanoimprint lithography. There is a lot of beautiful science involved here. So basically, it is limited. You cannot apply everywhere. So if you have a flexible substrate over which the polymeric material is coated, you can transform it for a roll-to-roll process. But what needs to be done? So you have a glassy polymer which is coated on another flexible substrate, let's say a transparency sheet or whatever. You bring it into the patterning zone, and now the master is now replaced with a roller which has the features, right? So the roller is rolling, this pulley is rotating in the reverse direction, and now there is a lot of engineering actually needs to be done so that when this film comes in contact with the roller, locally there has to be adequate heating so that the polymer melts. It sort of exceeds the glass transition temperature. What is glass transition temperature to an engineer or thermal science engineer? Glass transition temperature is a temperature above which the viscosity drops significantly, right? So that it exhibits more like a liquid behavior. And then you do the patterning, fair enough, no problem. But if you, again, leave this pattern surface, which is soft, right? What is going to happen? Again, it will try to flatten out because it's a liquid after all. So you not only have to achieve instantaneous heating over here, You also need to achieve very quick cooling right after the patterning zone to sort of achieve a roll-to-roll nanoimprint lithography. There is a lot of development that has gone in. There are patents, there are German companies who are working on this technology. There are groups in India who also work on this. Other major advantage of this soft lithographic technique, some of the soft lithographic techniques, particularly the ones involving flexible stamp, is unlike photolithography, where you could only pattern not only a photoresist layer, but the photoresist layer had to be spin coated only on a planar surface, right? But here, since you are using in certain cases a flexible stamp, so you can also like what is drawn over here, this is from one of my very old work, you can actually have non-planar geometries which are covered with this type of polymeric film, let's say a cylinder or a sphere or part of sphere or whatever, and then achieve some of this patterning. So here if you see, these are some images, these are camera images, not microscope images, of some curved objects, cylinders, spheres, etc. And what you see is the structural color. So that actually confirms that the patterns that you are trying to create span over a large area. So all these are some of the advantages. As I told, these are low-cost techniques for creating meso and nanoscale patterns over different type of surfaces with different type of material, right? So you can see some of those. Moving on, so far we have totally limited our discussion to topographic patterns, right? Now, one of the examples of chemical patterns that we talked about is alternating domains of hydrophobic and hydrophilic regions. And there is a very well-known technique called micro-contact printing, which is sort of rubber stamping, you can say, which can be used for creating alternating domains of hydrophobic and hydrophilic patches. So again, to implement this technique successfully, you need to know about one special type of material, which are basically a special type of polymeric material. Basically, it has two end groups over a polymer chain like this, right? Let's say X and S and X, or X and Y, or whatever. So one of the end groups binds them well with the surface, right? The other end group exhibits either a hydrophobic or is attached to a hydrophobic or hydrophilic end-terminated group. So depending on the nature of X, this can behave either exhibit hydrophobicity or hydrophilicity. Now these are one type of polymeric material, you can say, some polymers, so some thiols or silanes. So if you dispense them in a solution, right, and put in a surface, it's often a gold surface, only one layer of this molecule will attach to the surface. And which group will attach? The Y end will attach. So basically, you have these molecules, which only one layer of molecule will attach to the surface, and this is called the self-assembled monolayer. So you now take a surface, put it in a SAM solution, right? The self-assembled monolayer forms. It leads to a change in the effective wettability. What is meant by effective wettability? This surface is now covered with the SAM molecules. Now, if X is hydrophobic, then the surface will exhibit effective hydrophobicity. If X is hydrophilic, then the surface will exhibit effective hydrophilicity, right? So this is also a very interesting technique for changing or altering the wettability of a surface. Now, how can we combine this concept with that of soft lithography? So just see the video and I'll explain. What you do, you take a Silgard stamp and put it in this silent solution, right? And now bring it in contact with the surface to be patterned. So basically what is happening, unlike here, where the full surface is coming to the SAM monolayer, SAM monolayer is forming over the entire surface. Here what is happening is that as you take the stamp and put it in the solution, the stamp gets wet. So if you see carefully, there is actually the stamp, a thin layer of liquid surrounds the stamp. And when you bring it in contact with the other surface which you want to pattern, you bring it in contact. So now what happens? Only over these areas, the liquid and the solid come in contact. So now the SAM formation, the self-assembly monolayer formation, happens only over these areas, that is, these protrusions of the original stamp. In comparison to had you dipped the surface, so basically this is the same surface which you are trying to pattern. In the previous case, what you did was you took this surface and put it in a solution of SAM. So the SAM monolayer sort of formed over the whole surface and led to an effective change in the wettability, right? But here you are not dipping it into the solution. Instead of that, you are bringing in the solution with the help of another patterned stamp, and only in the areas where these stamp features are coming in contact with the surface, the SAM monolayer is forming, because only those areas it is coming in contact. The other areas it is not forming. So basically what is happening? What is happening is these areas, this drawing is a sketch is a little small. These areas where it did not come in contact, the original surface properties are retained. Whereas the areas where the stamp came in contact, you formed it, a layer of self-organized monolayers form over these areas. So now what has happened? Let's say the self-organized monolayer leads to hydrophobic properties. So only at these areas it now exhibits hydrophobicity, whereas as other areas it exhibits the original property. Let's say if it is glass or something like that, it exhibits hydrophilicity. And in the process, you are successful now in creating a surface that exhibits some property like this, alternating domains of alternating hydrophobic and hydrophilic domains. Now one may ask that how do you know that it is exhibiting such alternating properties? Well, again, one can use the atomic force microscope very cleverly to pick up this contrast in wettability, which of course, to keep things simple in the morning, I did not discuss. So here what we have shown now, that you now know that there is a technique by which you can also create chemical patterns, right? But there are some necessary conditions, like since you are using basically what you are doing, you are selectively exposing the surface or allowing the surface or allowing the SAM layer formation over the surface at selective areas. So certain parameters become very, very important. So if after you withdraw this stamp from the liquid layer, if it becomes too dry, right? So this stamp becomes too dry. Then what happens is when you bring it in contact with this surface, the molecules do not flow from the stamp to the surface because it has become too dry. So then again, pattern replication does not happen. On the other hand, if the stamp is very wet, right? So it is basically the smearing effect that you might have seen when you write with fountain pen, the same thing may happen. So if it is too wet, then not only the liquid sort of comes in contact over these areas, but the liquid may tend to spread more, creating structures which are wider. And in certain cases, the adjacent features might simply join up, leading to you do not see the patterns, but the whole surface gets covered with the SAM. So the extent of drying becomes very, very important in successfully achieving formation of chemical patterns. And this work is also a vintage from 1994. It was also published in the journal Science. There is sort of the last example I will take up from classical soft lithography literature is, so far, whatever, if you have understood, all the patterns that has formed is just a layer of pattern. So it's like one layer of pattern which you have created. So people started thinking, just the way people started thinking that can something be done by which soft lithography can be made continuous, people also started to think, can something be done by which you can create 3D structures by soft lithography, right? And there is another technique called micro transfer molding. Let me issue a statutory warning here. In soft lithography, as I told, that it does not refer to any single technique. There are large number of techniques which all are broadly covered into the umbrella of this topic of soft lithography. And many of them have names which are very similar to each other. But you need to, if you are interested ever in this topic, you need to really look into them very carefully, what they are. Because, for example, the previous technique of making chemical patterns was micro contact printing. And what we are now talking, which is a technique for making 3D patterns, is called micro transfer molding, right? So they sound very similar, but actually they are different. I will not go into the details of this, but here you use a photocurable polymer. So what you do is very similar to replica molding to start with. You take a stamp, you put this liquid layer, but there you took a thermocurable polymer. Here you take a photocurable polymer. And you do not just pour it, but you sort of, after pouring, scrape off in such a way that only the grooves get filled with the photocurable polymer. And then what you do, you expose this photocurable polymer filled grooves to some UV light or something, so that this polymer, this polymeric material that is inside the groove, it sort of hardens, right? Now what you do, you sort of just keep it upside down and swell it, not with some solvent, which swells the outside matrix, that is the replica molded Silgard 184. So if the outside matrix swells, so what happens, these individual sticks or threads that are formed in the groove, they detach and they get transferred onto a surface. And you can repeat this process again and again to basically build layers of structures, giving a 3D flavor to these soft lithographic features. So this is the literature part of soft lithography. I tried to give you some idea about what soft lithography is and what are the techniques. So now probably this slide will make good sense to all of you. Basically, we now know there can be techniques for making chemical patterns, for example, micro contact printing. There can be techniques, or there are techniques for making topographic patterns, which are like nano imprint lithography, replica molding, capillary force lithography, or in certain cases, even there can be techniques for creating three-dimensional structures like micro transfer molding, right? So now if you, again, let us go back, and if you now see this slide, this will make a much better impact onto you now. So you can classify all the techniques based on either you are using a soft stamp or a rigid stamp. For example, something like nano imprint lithography, where you had to apply external pressure, you required a rigid stamp. Or let's say some techniques like capillary force lithography, or micro transfer, micro contact printing, where there was no need for applying pressure. You could use a flexible stamp. This can be one way of classifying. The other way of classifying can be whether you are creating topographic patterns or chemical patterns. That is also clear to you. And now if you see, except mimic, I did not teach today, but other techniques, you sort of have an idea what they are. Right, so this is basically the first part, what I wanted to talk. And in a nutshell, now we know that photolithography, which is the most widely used patterning technique, is sort of limited to photoresists, which is essential for device application. But there are other applications with different type of polymers where photoresist may not be required to be patterned. Other type of polymer needs to be patterned, and for which you can use the soft lithography techniques. Now, the last 30 minutes or so, this is what I taught for the first 1 hour 15 minutes is more of a tutorial, what exactly people have done, so that you have a glimpse of what the subject is, what the topic is. But now I will give some idea about some of the research that is going on in my group. So the first problem statement we talk about is, if you look into the slide, now the left part of the slide is very clear to all of you. That is, there are multiple soft lithography techniques which are available by which you can create a perfect negative replica. But let's say I would like to create these type of line grading structures which have different feature height. So how do you do it? Normally, with your knowledge of what you have acquired so far in last 1 hour, you would say that if we have different stamps of different feature height, it can be done, right? Now, those of you who were also present in the morning, I was talking about the strength of the atomic force microscope, and there I told one example I gave where it is the only microscope that can actually give you the correct feature height. So this problem we are looking at is all about using an AFM, because without an AFM you can't even measure what is the feature height, right? So this is a direct application of what I was telling in the morning. Now the question that I very cleverly did not address and did not sort of encourage you to also think, even the first slide on replica molding, what I showed that you take a stamp and then you pour some liquid, you do thermal annealing, this and that. The question that is not answered is, where does the original stamp come from, right? Because soft lithography, you must have understood by now, is predominantly a secondary patterning technique. What is meant by secondary patterning technique? These days, of course, Xerox is becoming completely obsolete, but let's say even 10 years before, students used to Xerox notes of some students, right, who takes good notes or whatever. But in order to, the Xerox machine produces a copy of something that is already written, right? Because if you put a blank sheet, you will also get out a blank sheet. So basically the whole idea is of soft lithography or whatever we discussed so far is, if you have a stamp, techniques are available to create its copies, right? But the question to ask is, where do you get the original stamp? Turns out the original stamp has to be lithographically fabricated, and often it turns out that fabrication of the stamp is not that easy. It's quite expensive. So had you had very good fabrication lab, you can create different stamps with different feature height and apply any one of the techniques that you have learned. You can create these structures. But suppose, at least in my case, that was the situation, we just had only one stamp. Could we still solve this problem? And yes, we did solve it. How we did it? We used the physics of the material Silgard 184 that we talked about. What did I say? That it comes in two parts, part A and part B. And initially it's a liquid, it's a high viscosity liquid. And then when you do a thermal annealing, right, it transforms into an elastic solid. So there are two terms. So initially when you start, it's a liquid. Liquid means it's a viscous material. After the annealing is done, it transforms into an elastic material, right? So basically, what is this thermal annealing doing? Forget about the chemistry part of it. Even I do not know. The thermal annealing is basically transforming a liquid into a solid by means of development of these cross links, what I drew over there. So this transition must be through different stages of viscoelasticity. You know what is viscoelastic material? A material that exhibits partial viscous properties and partial elastic properties. Have you seen a door closure in an air-conditioned room, an automatic door closure? There are sometimes a door closure on the top. Have you seen? Right. So what does it do? It sort of, as you leave the room, it gently closes the door behind you, right? Many people think door closure contents of a spring, right? But had it been a spring, it would have accelerated as the door closed, and it would have every time it would have banged behind you. But that does not happen, right? It closes the door in a very gentle way. What makes the response so gentle? Because it contains what is known as the spring dashpot. This dashpot is basically a viscous fluid which damps the response, the elastic response of the spring. So that is the classical example, the Maxwell's example of a classical viscoelastic material. So what we realized that when we take that liquid and put it for thermal annealing, with progress in annealing, the material becomes more and more elastic. That means the viscoelasticity or the elasticity increases. Now, about an hour back, I gave the example of that rubber, right? You stretch the rubber, it relaxes back. Why does it happen? Because it's an elastic material. So the energy that you are using to deform it remains entirely closed, entirely stored within the matrix itself, right? Now think of a material which is partially viscous, partially elastic. So if you apply some energy from outside to cause deformation, part of the energy will remain stored within the elastic matrix, and part of the energy will dissipate because it's exhibiting some viscous properties, right? So now, if you have understood this, what we did was we have one stamp, and we took two films of the same Silgard 184 and pre-cured it for different durations. So as you pre-cure it for different durations, let's say one is pre-cured for 10 minutes, one is pre-cured for 20 minutes, probably now you understand that the one that is pre-cured for 20 minutes exhibit higher level of elasticity as compared to the other one which is pre-cured for a shorter duration, which exhibits more amount of viscosity rather than elasticity. Now what we do, we sort of follow the protocols of nano imprint lithography. We bring in the stamp, we apply pressure from outside so that we cause some in situ deformation. But nano imprint lithography, what did we do? We maintained the pressure till the pattern replication was complete. Here what we do, after we feel that the deformation is done, there are of course some details which I will skip. After the deformation is done, the pressure is withdrawn. So now what we have two films which are both deformed because you applied some pressure, right, or force from outside. And now suddenly there is no force that is being applied from outside. So the amount of energy that is stored within the elastic matrix will now relax. And amongst the two films, the one with higher level of viscoelasticity will relax more. So basically, what is the signature of this relaxation? The signature of the relaxation is as if the stamp is pushed upward. And what we could achieve is, again, the results are very convincing because we had an AFM. You now see that you can create structures which have the same line grating geometry, but each one has different feature height. And what is the trick? The duration of pre-curing was basically varied from film to film. So longer was the duration of pre-curing, right? Higher was the level of elasticity, and higher therefore was the level of stress relaxation. So once it becomes fully elastic, it does not deform at all. So in a nutshell, we actually could achieve creating patterns which are having the same line width but different feature height using a single stamp by cleverly utilizing the concept of viscoelasticity and stress relaxation. Okay, and now once we could do that, we thought of creating an interesting type of a structure that is a topographic gradient feature. Now, what is topographic gradient? If in the same film, one side has deeper features, the other side has shallower features, and you sort of have a continuous variation in the feature height from one end to the other. So what did we do? It was a very clever heat transfer approach, I would say. So far we have been talking about thermal annealing, right? So where was this thermal annealing being done? This thermal annealing was done by placing the film inside an oven. So if you put inside an oven, because of thermal convection, there was uniform heating, right? But instead of that, what we did now is we simply took a hot plate and we kept the film facing, not touching the hot plate because then it will become dirty, facing the hot plate with two spacer blocks which are of different height, right? So you create a geometry like this. Now this is the heat source. This part of the film, here is the film, the blue colored thing. This part of the film is closer to the hot plate. This part of the film is further away from the hot plate. So now I guess all of you understand that this area receives more heat flux as compared to the other area, right? And what is the consequence of that? The consequence of that is this part becomes more elastic as compared to this part, right? Now, if you try to do the same experiment, what I discussed in the previous slide, that is you take a stamp, apply pressure, deform. What have you created here? You have basically created a film with progressive viscoelasticity gradient. So now, unlike different films exhibiting different level of stress relaxation in the previous example, what will happen here is different parts of the film, same film, will exhibit different levels of stress relaxation. And this part, which is more elastic because it has received more heat, will exhibit higher level of stress relaxation as compared to this part. And therefore, in the process, you can create in one go a patterned film or a structured film which has topographic gradient. And there are a whole lot of control parameters. So exposure time becomes a control parameter. The difference in the height of the two blocks become a control parameter. In fact, if y1 becomes equal to y2, just by this way, it sort of becomes parallel to the hot plate and it becomes identical to the previous case. But here, this nice looking graph actually shows how by varying the pre-curing time as well as the depth of the individual blocks, etc., how different gradients, different extent of gradients. It's like y equal to mx plus c, and where m is different in different cases can be created. And here what you see is again a large glass slide where all over the place you can see the structural color, confirming that the patterns are present everywhere. Now this is done. What about the next? So what has been achieved? That if you consider this case, yes, we are successful, and I call this area as patterning beyond the master. This is a term I use, which probably you will understand, because most of the known soft lithography techniques allow you to make a negative replica only. Here it's a very frugal but deep in science approach, which allows you to create structures which are not limited to negative replica. Agreeing to that, you still realize that this method has a limitation. And the limitation is you can create any feature height, but the maximum feature height is limited to H0. That is whatever is the feature height of the original stamp. So we thought, if we can do this, can we create the other thing? You have a stamp with feature height, let's say HP. Can we create structures which are taller than that? And you know from where I got this idea? The idea I got is from a very simple thing that if you have a cut and use a sticking plaster, when your wound is healed and you want to peel off the plaster, you must have seen that a part of your skin initially gets pulled up along with the plaster before it peels off, right? And we basically encashed on that idea. Uh, what I taught in the morning also in the context of AFM, that is the intersurface interaction. So you just see what happens here. So what is happening is you have an elastic film and a rigid surface approaches it, right? Now what you know, because in the morning we also talked about it, as the two surfaces come very close to each other, there is active van der Waals interaction, right? And those van der Waals interaction, they are unnoticed in rigid objects because they are too stiff. But if you have a soft material or a soft film, you can actually see some undulations and features which are appearing on the film surface, right? And we have captured that microscopically. So just see the videos and then I will come back. Sorry, it did not open from the PowerPoint. So this is actually under an optical microscope. What happens is a transparent contactor is approaching a soft film. You are just doing nothing. You are just reducing the intersurface separation distance. And what you see, these type of features form, these type of random features form, spanning over the entire film surface. And if you approach more, you now see those bicontinuous labyrinth-like structures transform into individual holes. So this is a true microscope image. Right. So this is basically the cartoon, and you also saw the actual uh, patterns that form. So now you understand under what condition they form. And these patterns are random, labyrinth-like, but they sort of have a dominant wavelength, or the size of these structures sort of depend on their film thickness, which is pretty well established. Now, so these experiments, I'm skipping the science part of it, the detailed science part of it. But what is very important to note here is the film that you have is an elastic film. So it's more like a rubber band, right? So these features or patterns form only when the contactor is approaching. Only when the contactor is approaching, and once you withdraw the contactor, again the features disappear. And some of these pictures actually capture that. So this is during the bonding stage, where initiation of the instability is through some formation of pillars, then it transforms into these labyrinths, and then eventually these holes. And during the debonding phase, that is the detachment phase, you again see that you get these bicontinuous structures somewhere, then some columns, and then the two detaches completely. So all this was known, but nobody looked into one very interesting aspect, that if you look into these two images, you sort of see this labyrinth appearing here and also appearing here. So everybody talked about, okay, this is a reversible process, wonderful, the same patterns appear, disappear, etc., etc. But what nobody looked into was a more detailed AFM image of the same phase during bonding and during debonding. And now some of you who are present in my morning lecture are pretty good experts of AFM. So now you see the images look roughly the same, but what is different is the scale bar. So while the features are having a height of about 150 nanometer during the approach, exactly identical features appear during debonding, which have much higher feature height, right? So we decided to encache on this. So what we did, instead of a flat contactor, we now took a patterned contactor, right? We brought in contact. I will skip the details, not make things too heavy for you. But when we started to detach, basically the effect that I was telling, that the surface or what you saw here, why does it sort of form taller features? Because it is sticking, and before it debonds or detaches completely, a part of it is sort of pulled off. That what I was talking about, that sticking posture. And to cut a long story short, basically we take a patterned stamp, just the way we do for NIL or whatever, and then we first bring it in full contact, and then we withdraw it, and we simply freeze the structures by some little bit of tweak in chemistry, and we could create structures which are actually taller than the original structures. How do we convince? So this is the geometry of the stamp, which has a feature of 150 nanometer. But now you look at the geometry of what we got during detachment, it shows a very funny number, 420 nanometer, but the results are not 420. So we could create structures which are almost 2.5 times taller than the original stamp patterns. And that also leads to change in the weightability, etc., etc. We also did some very interesting in-depth studies, and one of the very fascinating results that emerged out is at the nanoscale, the coefficient of friction itself becomes a function of surface area. It turns out, this is almost like people will not even believe, but it turns out that there was a 2009 Nature paper which talked about this at the nanoscale, but which was never sort of validated. And our results sort of substantiated or validated those. There was some more part which requires a little bit in-depth understanding, so I will skip it. So not only in this approach, we could create structures that are taller than the original structures, but we could also sort of modulate the periodicity of the structures based on the fact that, one slide I did not emphasize, that the periodicity of the structures also depends on the film thickness. So by modulating the film thickness, we could sort of play with the periodicity also. So anyway, all this was achieved. Now the third and probably the last problem I will talk for today, I think I have been talking for 1 hour 40 minutes now, those of you who are listening must also be tired, is another very simple example of self-organized pattern formation that came out from Whiteside's group. And it is when you deposit a metallic layer on a polymeric layer, right? I guess, so what happens is, you take a polymeric elastic film layer and do a thermal deposition of metal, which is at a high temperature. And then as you cool down, you see some wrinkles appearing on the surface. So this is related to some very basic thing you have studied in your school days, and that is the bending of bimetallic strip. So you must remember that if you took the bimetallic strip and heated it up, while cooling it bent, because the coefficient of thermal expansions were different for the two materials. Exactly the same thing happens here, but it's for a thin film. So what happens is, this mismatch in the coefficient of thermal expansion is manifested in the form of appearance of some wrinkles. So what? So this type of wrinkles. So what people knew was this, just like the previous example, the wrinkle periodicity. So even the pioneering paper, it's around 2002. What they did was they took a fully elastic film, and on that the metal was deposited, and you can see these type of wrinkles actually appeared, right? But what we did was, based on our learning in one of the previous studies, that is to tailor the viscoelasticity. And what we could show, that by taking the film of same thickness but different level of viscoelasticity, if you deposit metal on them, you can create basically structures with different periodicity and geometry. So how do you create structures or films with different levels of viscoelasticity? You simply precure for different durations, what we already talked. So this was a very fascinating technique. So like, you have a film, same film thickness, you do not vary the film thickness or anything. All you do is you vary the duration of pre-curing. So for example, this one is fully cured, so it's a elastic film. These ones are partially cured, so they are viscoelastic. And in the process, you can create films or wrinkles which have different wavelength, right? Or they're smaller, bigger, whatever you want. Uh, so since we were doing detailed AFM analysis, we not only looked at their periodicity, but we also looked at their amplitude. The feature heights could also be tailored. And then we realized, of course, there's no theoretical model available for that, that the mechanism of the wrinkle formation itself was varying from system to system, right? If it was like a viscous film, the deformation was happening straight away during the film formation, whereas if it was fully elastic, the deformation was happening during cooling and stress relaxation. And for viscoelastic film, it was a combination of both, and therefore that could explain features with different periodicity and different amplitude. And as I talked in the morning, not morning, some time back, that if you have structures on a surface with different geometries, they often lead to different optical and wetting properties. So these surfaces with the different type of features that we created, we checked for their optical reflectance and their wetting properties. And you can see that the equilibrium contact angle or the water contact angle drastically varies as the geometry of the surface. And also here you can see these are some results from the spectrophotometer. But more importantly, here are some physical samples. And in certain cases, so these are like on the patterns were created over silicon wafer, which is shining, very shining. So you can see the reflection of this logo over here, right? But for this sample, you see no reflection at all, right? So what has happened is, by tweaking or modulating the geometry of the features, we could actually control the reflectance of these surfaces or whatever, which is very, very important in many applications. For example, this particular one, you can look into the publication for the details, is created a completely non-reflective surface. And I was talking about the example of the glass cover in a solar panel, right, where anti-reflection property is extremely desirable, because when sunlight falls on the panel, you want the entire amount of light to transmit to the active layer. You do not want the light to get reflected away. So these are very simple concepts and works, but they have huge and significant consequences, and they are all very low cost techniques, right? Yeah, so this is the last story. Again, for an undergraduate group, you may not exactly know what TEM grid is. So TEM is another type of microscope, transmission electron microscope. As the name suggests, transmission electron microscope is like you take a thin slice of material and through which an electron sort of electrons pass through, and as they passes through the electrons, they gather, since they are passing through the material, they gather information about the structure of the material. Now I'm not going to talk about transmission electron microscope, though IIT Kharagpur has one of the finest ones in the country. But there are some small metallic grids like this which are available for holding these samples. They are very low cost things, you can say, over which the samples are placed and put in the microscope. So these are again poor man's or poor people's stamp one can use for doing some nice patterning work. And there has been some work. So these are like metallic meshes like this. So you have some cross meshes as has been shown over there. So what a lot of people did before is that you take an elastomeric film, you place a temp grid and do an UV exposure. So what happens is this, remember I told this Silgard is a silicon based polymer. So this polymer, if it comes in contact with ultraviolet light, there is actually in situ dissociation of atmospheric oxygen, which combines again with oxygen to form ozone. And this ozone actually reacts rather violently with this polymeric material, leading to some oxide layer. Right now, this oxide layer is also associated with some compaction. So what happens is these zones below the grid, they do not get surface oxidation, but the areas that are exposed, they are subject to surface oxidation. So consequently, what happens is if you simply place a grid over a Silgard elastomeric film surface and just put it under UV, you get some cross patterns like this. So this people knew for a long time. And people also thought that this is entirely a surface phenomena. So the depth of the grooves or whatever only depends on the duration of exposure. So this was rather well known. So basically, if you see over here, you can see that these areas which are below the unexposed areas, there is an oxide layer formation, which is also associated with a volume compaction, which is presented in the form of these features. What we did was we took now films of different thickness, and to everybody's surprise, nobody expected this to happen. To everybody's surprise, we realized that the depth that we were getting for the same duration of exposure was a function of film thickness and also the function of cross-linker concentration, that is the extent of elasticity. So to cut a long story short, this is the last thing, we have been talking for a long time. What we realized is this aspect has been completely overlooked. The reason for that is people thought this is anyway a surface phenomena. So whatever modification is happening to the surface, that is the only important thing. But what we showed that as there is UVO mediated compaction, the propagation of this compaction front deeper, right, becomes a function of how far the bottom rigid substrate is, the boundary is. So if you have something which is or I don't exactly recall a practical example how to correlate. So basically what we realize that these areas where the grid is open, those areas once upon exposure, you create these type of depleted zones, and basically those areas the oxide layer forms, and the oxide layer actually the compaction is associated with the penetration of the oxide layer along the depth, and this depth, how far it can go, is sort of hindered by the presence of the underlying substrate there. And therefore we could again show that by simply varying the initial film thickness, you can create or control the depth of the patterns again. So the whole idea is that you start off with a single not exactly a master over here, but a single geometry, that is the 10 grid geometry. And by varying the film thickness, you can now create structures which are of different height. We could also show some relaxation happening for films which are more elastic, but I think I will skip for that. And this data was captured using very careful atomic force microscopy, scanning the same area again and again over a period of time, exhibiting that there was relaxation due to the stress relaxation or height relaxation. I think I have sort of come to the end of my talk, but as I told that there are a lot of applications of these pattern surfaces which are not only for device applications but other applications. So here, for example, there is an example of some work I have been doing with a colleague of mine. The student is now settled in US, who earlier worked with me. So where we showed that proliferation or growth of some cells can be significantly modulated over these pattern surfaces. Some more work on that. And one of my students also did some photo detector, developed on photo detector based on some soft lithographic techniques, and could enhance the performance and the response of it. So with that, I think I will conclude my talk. And basically what I talked about is, gave you a brief idea about patterning, which is again a major microfabrication technique for polymeric material, which falls under the broad category of soft lithography. And now you understand that photolithography is essential, but photolithography is more oriented towards device applications, and it can work only for photoresists. But there are wide variety of polymeric material which can be patterned by different, very creative, very niche scientific techniques, right? Which all fall under the broad category of soft lithography. And then there can be different techniques which can lead to either topographic patterns or chemical patterns, etc., etc. And some of these, if you now come across, it will make some sense on you about molding, micro molding in capillary, nanoimprint etc. And then after understanding bit of it, we realize that the soft lithography techniques are capable of creating a perfect negative replica of a stamp, which has to be lithographically fabricated somewhere else. So the second part of my talk, the last 35 minutes or so, I focused on being more creative. That is, you have a single stamp, and then with that you can create different structures. And some of those novel examples I showed. These methods are simple, very easy to execute. You do not really need very big infrastructure. They are scalable, creative, and involve very rich physics. And I also talked about some potential applications. So these are my students who have done all the work, which I just presented to all of you. And hope you learned something. And thank you very much from IIT Kharagpur. Thank you. So, I don't think you will have questions because this is something that is slightly away from what you have been studying. But if you are interested, these are all getting recorded. So if you want these, you can look into it. And there are many applications where you can find many engineering applications of these patterns, and which can be interesting.